Let's take a look at a few more of these work energy theorem questions. And for this first problem, we have a 250 kilogram roller coaster and it's going through points A and B with the following speeds shown in the diagram below. And our goal is to find how much heat energy is produced between these 2 points. Okay, so since we're starting at position A, we notice that we're given a height and initial speed. So what that means is we definitely have kinetic energy and we also have potential energy. Now, when we finish this problem at point B here, we're given a final speed, so that definitely means we have some kinetic energy. But since we're at the bottom of the incline, there's no height, so that means there is no potential energy. All right, so that's how you can kind of analyze this initial problem. And then we jump down to the work energy theorem, which states that energy is conserved, and that means the energy at the beginning is equal to the energy at the end. So the beginning is denoted by the letter A, and the end is denoted by the letter B. Okay. All right, so as stated at the start of the problem, we did have some potential energy and kinetic energy, and since we're trying to find how much heat energy is produced, we want to save this h variable right there, and we can just eliminate the work variable because this question states nothing about work energy. Okay, now at the very end, we're given a final speed, so we definitely have some kinetic energy, but we don't have any potential energy at position B because there's no height. Okay, now if we start converting the symbols into their formulas, we know that the potential energy here is really your mass times the acceleration due to gravity times the height. All right, plus the kinetic energy at the beginning, which is 1/2 mass times the initial speed squared, then minus the heat energy, and that's going to equal to the kinetic energy at the very end. So 1/2 times the mass times your final speed all squared. Okay, and then from here on, we're going to just plug in some of the numbers here. So if I go back to the original problem, the question states that we have a 250 kilogram roller coaster. We have an initial height of 18 and an initial speed of 4.5. Okay, so let's go ahead and plug in those numbers now. So I'll use a red marker here. So the initial mass of the roller coaster here is 250 kilograms. The acceleration due to gravity was 9.80, and the initial height of the roller coaster was 18. Okay, and then we're going to add the kinetic energy at the beginning here. So the kinetic energy we have is going to be 1/2 times the mass, which is going to be 250. And the initial speed was 4.5, and we raised it to the power 2, and then we minus our heat energy. All right, so that's all the energy. Those are the numbers that we need to consider at the beginning of the problem. And at the very end, we are given the kinetic energy at the very end, which is 1/2 times the mass, which is 250. And if I go back to my diagram, my final speed was 15, right? So this is going to be 15 meters all squared, meters per second all squared. Okay, so let's go ahead and start calculating the numbers here. So if I multiply these numbers out, my potential energy is going to be 44100 joules plus, and then I calculate my kinetic energy there, which is going to be 2,531.25 joules, and then I minus my heat energy, and that's going to equal to my kinetic energy at the very end, which is going to be 28,125 joules. Okay, and once we solve for our heat energy here, all right, so what we're going to do is we bring the heat energy to the right hand side, and I take this 28,125, I bring that to the left hand side, and if I go ahead and just add the numbers and then subtract my kinetic energy at the very end, I get 18506.25 joules. So that is the amount of heat energy that was produced in this particular problem. Here's another similar roller coaster problem. So we have a mass of 250 kilograms for the coaster, and it starts at point A, which is right here, and then we finish at point B. And the question is stating, what is the speed of the roller coaster at point B at the bottom of the hill if we have 8,500 joules of energy, which is transformed to heat during this journey. Okay, so we want to find our final speed at the very end, and we're also given this amount of heat energy that's produced during this problem. Okay, well, at the beginning, I noticed that we have a height here, right? So what that means is we definitely have some potential energy at the beginning. We're given this initial speed, so that means we have some kinetic energy at the beginning as well. And at the very end, when we're at point B, there's no height, so let's just say that there's no potential energy at the very end. Okay, so that's how you can analyze this initial, this is how we can analyze the diagram right here by looking at the numbers. And then we can go into the work energy theorem right here, which states that energy is conserved. So the energy at the beginning is equal to the energy at the end. And the letter that we're using for the beginning is the letter A, and we're also using letter B to represent the very end. Okay, so we definitely have potential energy at the beginning because we're given a height of 18 meters. And we also have a kinetic energy at the beginning because we're given the initial speed. And the problem also gives us a little bit of this heat energy right there. But since the question states nothing about work, we can get rid of the W there. And there's no potential energy at the very end because we're at the bottom of the hill, but we do need to calculate the final speed, so therefore we need to calculate the kinetic energy at the very end. Okay, so go ahead. Once again, so once we convert these into their formulas here, your potential energy is mgh, your kinetic energy is 1/2 mass times your initial speed squared minus your heat energy, and that's going to equal to your kinetic energy at the very end. So 1/2 mass times your final speed all squared. Okay, and then from here on, let's go ahead and plug in the numbers here. The mass of this roller coaster was 250 kilograms. The acceleration due to gravity was 9.80. The height that we're given for this particular problem, as mentioned, was 18 meters, right? And our initial speed was 12. Okay, so this height is going to be 18. And then if I move on to my kinetic energy, I have 1/2 times the mass, which is 250. And the initial speed here was 12, so 12 squared. And then let's take a look at our heat energy. This is actually given to us in numerical form right there. So there's our heat energy. So we need to subtract the 8,500 joules of energy. And then that's going to equal to our kinetic energy at the very end, which is 1/2 times the mass, which is 250. And then we've got to find our final speed, and that's being raised to the power 2. Okay, so a lot going on there. So we definitely need to crunch out all these numbers here. So if I go ahead and find my potential energy at the very beginning by multiplying those numbers out, I get 4,100 joules plus, and then my kinetic energy at the beginning is going to be 18,000. And then I minus my 8,500 joules of energy, which is given to me at the start of the problem here. And then if I go ahead and multiply 1/2 by 250, that gives me a value of 125, and I need to find my final speed all squared. Okay, so that's the goal right here, to find the VF there. Okay, if I go ahead and continue here, if I add up these two numbers and then subtract the heat energy, I get 53600 joules, and that's going to equal to 125 times my final speed to the power 2. Then I can divide both sides by 125, so on the left hand side I get 428.8, and then to get rid of this power 2 here, I can just simply square root that, and then I can square root that. So square root both sides, and then on the right hand side I finally have my final speed, and this is going to be equal to 20.707 meters per second. Okay, so if I go back to my diagram here, I just want to say that my final speed here is equal to 20.707 meters per second. All right, so that's my final speed at the very end of this particular problem. If we continue along with the work energy theorem concept, we do have a few more of these word problems. So in this word problem, I have a 1,500 kilogram plane initially at rest, and it leaves an airfield, and a short time later, it is at an elevation of 3,200 meters, traveling at 65 meters per second, and we want to find the minimum work done by the plane's engine in this time, and then we ignore air resistance. Okay, so a lot going on here. So let's go ahead and collect some information first. We know the mass of the plane is 1,500 kilograms. It's initially at rest, so that means your initial speed is equal to 0. And what that really means is that there's no kinetic energy, right? No kinetic energy at the very beginning. Okay, and then a short time later, it's at an elevation of 3,200 meters. Okay, so that means the height above the ground a short time later is 3,200 meters. And your final speed for this particular problem is going to be 65 meters per second. And we've got to find the minimum work done, right? So we're going to find the work done. And we ignore air resistance. Okay, so let's go back to the work energy theorem concept, which is stated right here. So that means energy is conserved. So energy at the beginning is equal to the energy at the very end. Okay, so since we have no initial speed, that means we have no kinetic energy, right? And since we're on the ground, right, it's leaving an airfield, right? So technically the plane starts on the ground, and then a short time later, then it's at an elevation of 3,200 meters up in the air, right? So since you're on the ground, that means there's no potential energy at the beginning, all right? And the question also tells you to ignore air resistance, so let's get rid of the H there. And since we have a height, 3,200 meters, we definitely have potential energy at the very end. And since our final speed is 65, we also have kinetic energy at the very end. Okay, and our goal is to find work. All right, so by using the work energy, the work energy theorem here, we know that if I isolate for my work now, it's really equal to your potential energy, which is mgh, plus your final kinetic energy, which is 1/2 m times Vf all squared. And all we're doing here is we're just kind of plugging in the numbers now. So the mass of the plane was 1,500. The acceleration due to gravity was 9.80, and the height was 3,200 meters up into the air. And then we have our kinetic energy, which is 1/2 times the mass, which is 1,500. And the final speed was 65 meters per second, right? So I just changed this to 65 meters per second, all to the power 2. And then there you go. You just need to go to your calculator now, calculate your potential energy and your kinetic energy, and you would just add those two numbers together there. So this actually gives, these are actually some pretty big numbers. So 4, 7, 0, 4, another 0, and then 3 more zeros. Plus, I guess I'm at 3 millionths, so 3168, and then 750 there. And then if I add the two energies together, okay, so I'm just going to round this to scientific notation here. Actually, hold on, it's 502.08750 joules. And then if you want to round that, change this to scientific notation, it'd be 5.0 times 10 to the power of 7 joules of energy there. Okay, so that's the amount of work you need for this particular problem. Let's look at another variation of one of these word problems. And for this problem, we now have a 5,500 kilogram aircraft initially at rest, and takes 920 seconds to climb to a cruising altitude of 9,500 meters. And we reach a speed of 210 meters per second, and we want to find the minimum average power required from the aircraft's engines during this time. Okay, so let's go ahead and collect some information again, just like the previous problem. So this mass is going to be 5,500 kilograms. The initial speed is going to be 0. This really means there's no kinetic energy. And then the time for this problem to reach a high, it takes 920 seconds to reach a height of 9,500 meters. And our final speed for this particular problem is 210 meters per second. And we want to find the minimum power, right? So eventually we're going to find the power, right? Okay. Okay, so going back to the work energy theorem concept, energy is conserved, so energy at the beginning equals to the energy at the very end. Okay, so since there is we're starting at rest here, that means there's no kinetic energy. And since you're on the ground at the start of this problem, there's no potential energy. Okay. This question doesn't really say anything about heat energy at all, so I guess we can just get rid of the heat there. And since we got to find power, we definitely need to find the work done in order to calculate power. So let's keep work on the left-hand side. And since this plane does elevate to a height of 9,500 meters and a final speed there, we have our potential energy and our kinetic energy at the very end there. So what we're trying to say here is now from the work energy theorem concept, we have work equals to, and then on the right hand side we have our potential energy, which is mgh, and our kinetic energy, which is 1/2 times the mass times my final speed squared. Okay, and then after that we can plug in the numbers there. So the mass of this plane is 5,500. The acceleration due to gravity is 9.80. And the height that we reached was 9,500. Plus 1/2 times the mass, and the mass was 5,500, times the final speed, and the final speed here was 210, right? So we take 210, then we square it. Okay, so this is going to be a pretty big number here. So once again, if you go to a calculator here and punch this in, this is the number I get. 2, 5, and 3 zeros. And this is the amount of joules of work, right? And this question is asking for power, and we know power is equal to work divided by time. Okay, so we know power is work divided by time. So if I just change this W to a power, and we know this is your work, we can now divide this by your time, and the time for this problem was 920 seconds, right? So we can divide this by 920 seconds, and then our power is now in the range of 688,396.74 watts. So joules divided by seconds is going to be watts, and if you wanted to just write this in scientific notation, it would be 6.9 times 10 to the power of 5 watts. All right, let's take a look at another one of these word problems again, and we have a 45 kilogram steel ball that's projected vertically with initial speed of 280 meters per second. And while the ball is rising, we have 8.5 times 10 to the power 5 joules of heat energy produced due to air friction. And we want to find the maximum height reached by the ball here. Okay, so if we collect some information here, the mass is going to be 45 kilograms. And our initial speed is going to be 280 meters per second. And that generally means if you're given an initial speed, you can definitely find your kinetic energy at the beginning. And then heat energy produced in this problem is 8.5 times 10 to the power of 5 joules. And we want to find the maximum height reached by the ball. Now, if the ball's on the ground and we reach a maximum height, which is at point B, there's actually no final speed at position B, because once you reach a maximum height, your final speed is always equal to 0 there. Okay, and we want to find the height for this particular problem. Okay. All right, so once again, using the work energy theorem concept, we know that energy is conserved, meaning that the energy at the beginning is equal to the energy at the very end. Okay, now when we're at the beginning at position A, the ball is on the ground, right? we're on the ground there, so you got to be very careful with this one here. There's not going to be any potential energy at the beginning. However, we do have some kinetic energy. The question doesn't say anything about work, so we can get rid of that. The question does give us some heat energy information, and I would say that since at the very end there's no speed, there's definitely no kinetic energy, but we have to find the height, meaning that there's potential energy at the very end. Okay, so looking at the work energy theorem concept here, since we have kinetic energy at the beginning, we need the formula 1/2 times the mass times your initial speed squared minus your heat energy, and that's going to equal to your potential energy at the very end, which is just mgh on the right hand side there. Okay, okay, so let's find the mass here. So the mass, as mentioned, was 45. So if we go ahead and plug in the numbers now, we have 1/2 times the mass, which is 45. And the initial speed of this problem is going to be 280 meters per second. So bracket 280 meters per second all squared minus the heat energy. And the heat energy is this number right here, 8.5 times 10 to the 5. So 8.5 times 10 to the 5. And that's going to equal to the mass, which is going to be 45 times the acceleration due to gravity, which is 9.80. And then we're going to find our maximum height right there. Alright, so we should definitely have enough information to figure this out. My kinetic energy at the beginning, if I use a calculator, I get 1764000, and then minus the 8.5 times 10 to the 8. And then if I multiply 45 by 9.80, I get 441 times my height. Okay, so 441 times the height. And then on the left-hand side, I get 914,000 joules. And then you can just divide both sides of the equation by 441. And if we do that, I get 2072.56 meters. And if I just round it up to a whole number, I guess, or a nice and clean number, I get 2,100 meters, which is my maximum height. Okay, so that concludes this homework video guide.